Right. Okay. Hello. Good afternoon. Welcome to Warsaw University Astronomical Observatory Tuesday seminars. And today we have a guest from neighboring institute, CAMK, Alex Markowitz, who has been here in Warsaw since 2017, but it's his first time since. So we're very pleased to have you here. Just a quick view on our guest. He did his bachelor at Berkeley, and then worked at the National Radio Observatory in New Mexico. Alex did his PhD in UCLA in Los Angeles, studying X-ray variability of sacred AGNs, and then worked at NASA as NASA postdoctoral fellow in Maryland, and then also in University of California, San Diego as a research scientist. And now was also a Humboldt fellow in Bamberg, and is working as associate professor in CAMK since 2017, and is going to tell us about X-ray observations. Alex, please.
Thank you, Akash, and thanks for inviting me to give a talk here. I really appreciate it. Thanks. So I'm going to talk about X-ray-Selected AGN Transients, which is it's our term for a range of categories of extreme variability in AGN that could be associated with, as I'll talk about, changing state AGN, changing look AGN in the optical, flaring AGN, and some other things. So this is work that I've been doing in collaboration with the eROSITA German consortium. So many co-authors to mention. So what I'm going to do is start off with just a general introduction to AGN and extreme variability in AGN, and then talk about the eROSITA X-ray Observatory, X-ray telescope, and then go into some of the specific AGN transient events that we've been working on. And particularly for the first third or so, this is actually the first time I'm presenting these slides, so if everyone has any feedback for things to improve, feel free to talk about it after the talk is over. So just very generally, we probably don't have to spend a whole lot of time discussing evidence for accretion on the supermassive black holes. It's been known in our field for a while. In AGN and quasars, we have 10% of them very large radio jets. We have thermal emission from the accretion disk. For those if you're like me, you do X-ray variability and X-ray spectroscopy, then studying the iron K alpha emission line at 6 keV and how when it's emitted from the inner accretion disk, you got the relativistically broadened and forms nice big profiles like this. That's of interest. Masers trace out the accretion disk. And in quiescent galaxies as well, we know they're black holes, mainly from gas dynamics, modeling, for example, molecular gas disks and individual stars. In the case of our own Milky Way, or bulk stellar dynamics in the case of both quiescent and active galaxies. Other galaxies. So the observational evidence is pretty well established, but the question is, how do black holes grow? And they get fed somehow.
Just a second. Just a second. Lost the cursor. Now you should be in control.
Okay, cool. So just to give a very general overview of some of the different types of accretion onto black holes, and this is not meant to be a complete picture, but just to give an idea that there's a lot of evidence for different types of accretion flows depending on how much there is relative to the Eddington limit. The Shukai-Sonura 1973 standard disk, geometrically thin, optically thick, radiatively efficient, is sort of one of the dominant dominant modes of accretion, particularly at what I would call intermediate levels of accretion, is you go to higher accretion rates relative to Eddington, you may get these more puffy disks, slim disks, towards much lower accretion rates, less than 10 to the minus 2, 10 to the minus 3. You may get something that's more radiatively inefficient, REAP for the convection-dominated accretion disks. And at really, really low levels, if you're considering something like Sagittarius star, maybe bond accretion, stuff that's just sort of tenuously diffusing on. So there is a wide range of accretion states. And if you study black hole X-ray binaries that go into outbursts, it's pretty common to see things transitioning, for example, especially between the thin disk and something where you have a radiatively inefficient disk in the center regions. If you don't study black hole X-ray binaries and you study supermassive black holes, and you're dealing with much, much, much longer timescales, so long that we really don't have observational constraints on how long accretion episodes last. Just from theoretical arguments and on the basis of things in the galaxy at kiloparsec scales, being able to funnel material inward, accretion episodes may last 10 to the, call it 5 plus or minus 1 years. But this is not at all constrained by observation, at least not yet.
Sorry. Why?
Am I doing this or you? Okay.
Try now. Yeah.
Okay.
Yeah.
Okay. So before we get into that, just sort of want to review the basic parts of the secret AGN. It's pretty much law that every AGN talk has to have a picture of something with a donut-like torus and showing the VLR clouds and showing how this can be used to support orientation-dependent unification. So we're specifically just reviewing the basic parts of the AGN. So black holes in the middle, we have the accretion disk. Maybe it's being fed by this torus, which the classic picture is something that's nice and donut-shaped and smooth, and a more updated picture is something that could be relatively more clumpy and filamentary and cloudy. I've done a lot of work on that, but it wasn't worth changing the picture over. Let's see. And you have an outflow, it's thought to be an outflow in the form of clouds that are pretty close to the black hole and relatively dense in terms of number density, and they emit very strongly in the optical range, yielding emission lines that in some cases are seen to be relatively broadened, and in other cases are relatively narrow. So basically this is that you have these two regions, the broad line region and narrow line region, from where in the optical spectrum, you can see, for example, there's a broad H beta line and a narrow H beta line in the top and bottom respectively. So the narrow lines are only broadened by a few hundred kilometers per second, and they tend to come from maybe kiloparsec scales. And the broad line regions are broadened, Doppler broadened to only a few thousand kilometers per second. And they are thought to occur much closer in. So the mystery is, in some objects, which we classify as type 1, why do you have both broad lines and narrow lines, and then in other objects, you only have the narrow lines, they're missing the broad lines? But a lot of observational astronomy is classifying things into a type 1 and a type 2, and maybe if you find more objects, there are subtypes. So a lot of ways to describe this. One of the classic methods is that the type 2 objects are blocked by some sort of material that contains dust, and it completely obscures the broadband region. The parsec scale torus is one possibility. There was a nice paper by Matt Malkin et al. 25 years ago, where they used HST to just do a snapshot survey of the host galaxies of nearby AGN, and found a good correlation between the prevalence of type 2s and being blocked by dust at kiloparsec scale. So that would be another way to turn a type 1 into a type 2. But in more recent years, there's also been the idea that the difference between a type 1 and type 2 might be an evolutionary sequence, which depends on volumetric luminosity relative to Eddington. So papers led by Moshe Litzer and Lewis Hull over the last decade suggest that the BLR is sort of an outflowing wind that simply may not be sustained below a certain value of the accretion rate relative to Eddington because there's not enough material coming in to be supportive of an outflowing wind. So this plot over here is just showing that if there's higher luminosities, you have more of the broadline regions, and the type 1s, and then the type 2s are more towards the lower luminosity range of things. So there are a lot of cases where a type 1 object a type 2 object is found to be a type 1 object in that in the optical spectrum you don't see the broad lines unless you look in polarized light or infrared light, and then you do see the broad lines, and yes, you know there is a broad line region, it's just hidden. But there are a lot of these so-called true type 2s where there is just no broad line region. It's just not there. And these seem to be more towards the lower luminosity end of things. So let me put that aside and just very briefly discuss variability. So I've worked with continuum variability, especially the X-rays, for a long time. So what I want to do first is introduce the idea of variability associated with persistent accretion. That even when you have one accretion mode and there's nothing changing on long time scales, you still have a lot of continuum variability. And these are associated with various mechanisms in the disk. One of the leading models is one where you have local perturbations in the mass accretion rate, moving inward in radius and modifying successively smaller and smaller radii. So on the left, I just took a couple of light curves from the RxCE database. So X-ray variability by factors of a few on timescales from hours to a decade or more is pretty common. I'm sure a lot of people here have seen the oval light curves. The optical is not as variable in short timescales, but surely towards longer timescales, you get factors of a few or more pretty easily in timescales of a decade or so. So the point is that even when you have normal sustained accretion, you still get strong variability. And I'm bringing this up because I want to contrast that with extreme variability, which is basically variability in excess of this, which indicates some big change in the state of things, in the state of the accretion flow. And in particular, one of the major things that can happen is you have a transition between different levels of the accretion rate relative to Eddington, like we see in black hole X-ray binaries. Like I said here, for those of you who study X-ray binaries, this is not really novel. People have been studying the outbursts and decays for a long time, but in AGN, this is relatively new, mainly because the transitions take a long time to detect. So one type of changing phenomenon we refer to as changing look AGN, where the look refers to the optical spectrum. And these are objects where the optical spectrum type changes between type 1 and type 2 on timescales of a few years or longer. And basically, the optical spectra show the broad emission lines fading or reappearing on timescales of a few years. And on the bottom, I just have a couple example plots. So just to take this one on the right from Shafi's paper 2014, I think this is 2617, right? So the broad line from the 1990s to 20 years later, the broad lines appeared, and these changes are usually accompanied by major changes in the continuum in both optical and X-ray, usually by factors of 10 or 30 or more. And these are, in these cases, you can roll out obscuration most of the time, and they can be driven by major changes in the accretion rate relative to Eddington. And that the accretion rate is changing, leading to major changes in the continuum. The UV continuum, in particular, is that ionizing continuum provides the photons to ionize the gas and produce the optical broad lines. And so there's a connection between the continuum changing and the optical spectrum changing type. So these are our first clues into the duty cycle of AGN, which is still relatively unknown. And it's also insight into the parallels between how accretion modes might change in AGN and how modes might change in black hole X-ray binaries. The problem is that they occur so rarely on a per object basis. You can stare at one object, and if you're lucky, after 100,000 years, maybe the accretion flow will change. And the need is to amplify these small numbers by going to big data and looking at large numbers of objects that you can monitor all at once. And so there have been a lot of good programs in the optical, Wiki Transient Facility, Catalina Real-Time Survey, Pan-STARRS, Gaia, and STSS as well for identifying CLAGN through spectroscopy. And so far we have about 150 changing look AGN events known so far. The number is increasing all the time, so this number may already be out of date. And transitions typically take a few years to a decade, it seems. But there are some additional open questions that we're still trying to answer. Number one, during these transitions, how does the accretion flow change? Well, how do the various structural components react? How long do transitions take? And in particular, one thing that we're interested in is how do these various structural components, the broadline region, the disk, the X-ray corona that emits the X-rays, how do they all interact with each other during these major changes in accretion rate relative to Eddington? And of course, what mechanisms are at work? This is also an open question. So this is a whole open can of worms into what type of mechanism might be at work, what type of instability might be at work, radiation pressure instabilities, propagating hot or cold fronts in the disk. This is all a fun topic to go into. In addition, more questions. Is it the case that the broadline region really does exist only above or below a certain value of the accretion rate relative to Eddington? That is, if you can track an object whose accretion rate moves up and down across its threshold, then you might expect the broadline region to appear and disappear and basically witness formation of the broadline region or its dissipation. And so even something like trying to get the geometry of the broadline region could be a wonderful thing to try and do, especially as a function of accretion rate relative to Eddington. For example, just to take a paper by Moshe Litzer, the idea is that when you go towards lower volumetric luminosities, the clouds with higher elevation disappear, and you end up with something that's more disk-like and much more hugging the disk. And so your measured covering fraction will decrease. And so there have been some various papers that do suggest that the majority of change look AGN seem to hug certain relatively low values of the accretion rate relative to Eddington, typically of order 1% or so, and not too far away from this inferred limit that Electra and Hill set up in 2009. So this does seem to be a, let's call it, it's not necessarily an open question, but it does seem to be, we are sort of moving towards answering this. So I've talked a lot about the objects that we've known so far and mainly have detected via optical surveys. Many of these objects have been identified relatively serendipitously in optical photometry and spectroscopy programs. But ideally, to make the best progress and track how the various components appear and disappear and rearrange themselves during an event, you need to catch events in progress and apply multi-wavelength monitoring to monitor the emission from all the various components. And the best way of doing this is to monitor a large sample of objects and identify events in progress. And as soon as you identify and confirm something, then you can initiate multi-wavelength follow-ups to track the optical UV continuum, get optical spectroscopy, X-ray spectroscopy, to track the disk and raw line region and X-ray corona, respectively. And that's what we're doing with eROSITA. The difference is that with eROSITA, we work with the X-rays, and we're trying to use the X-rays as a channel to catch new events in progress. And so with eROSITA, as I'll show in just a minute, we're doing bulk X-ray monitoring of about 1 million AGN to monitor them and look for new nuclear, it's called extragalactic nuclear transient events, including changing like AGN. So let's talk about eROSITA. So eROSITA is an X-ray telescope. It's the primary instrument aboard the Spektrum Renton Gamma spacecraft, which is a joint Russian-German spacecraft. It was launched in 2019 from Kazakhstan out into L2 orbit. And the main goals were to do multiple all-sky X-ray surveys in order to basically map out hot gas and trace large-scale structure of order of 10 to the 5 galaxy clusters, and trace the evolution of large-scale structure as a function of redshift, and detect 1 million AGN in the X-rays. So it has 7 X-ray cameras that operate in the range from 0.2 to above 5 keV, a common field of view of roughly a degree. And basically, the way that it works, I'll explain in a minute, it does one all-sky scan every 6 months. And so, I want to point out this nice pretty picture that was released by the eROSITA team towards the end of ERAS-1, basically showing that eROSITA has detected more AGN, more compact, more point sources in its first year than all of X-ray astronomy beforehand, if I'm not mistaken. So, like I mentioned, we're monitoring 10 to the 6 AGN. The way that eROSITA works is that basically its solar panels are always facing the sun, and it traces out a great circle once every 4 hours in a circle that is perpendicular to the sun. And so this whole thing just rotates as Earth and L2 move around the sun. And so you basically get one ring every 4 hours, and that ring rotates to cover the entire sky within 6 months. And this allows you to do X-ray time domain science for 1 million AGN. You get 1 point every 6 months, and you get 1 million light curves. So it started its mission in December 2019 and had done 4 1/3 scans by February of 2022, and then cooperation with the Russians was suspended following the invasion of Ukraine, and so eROSITA has been in safe mode since February of 2022. And so as of now, we're just working with the objects from the first 4 1/3 ERAS scans. So like I mentioned, eROSITA is a channel to detect in the X-rays events as they're occurring, basically by just comparing fluxes from successive scans. So just in the bottom, just to show you, here's one example of an object. Here are four ERAS scans, just showing the increase in X-ray brightness over a time scale of a year and a half. And when we detect something major, X-ray flux change it's kind of a soft boundary, but ideally 10 or 15 or more. But we're netting candidates by looking at what are 8 or more. And we then assign resources, as I'll talk about in a minute, to do multi-wavelength follow-ups and track the responses of the various components. So, but I do want to mention that there are additional types of events that we're interested in. So our group specifically does not do QPEs, but folks at Max Planck Institute certainly are. But with eROSITA, there have been a couple of what's called quasi-periodic eruptions, QPEs. So these are objects that show these very strong spikes every, 10 hours. They've been detected in only 5 objects so far. Two of them have been discovered with eROSITA. So I just want to mention them as an object that the community is interested in using eROSITA for, just in terms of taking advantage of eROSITA's time domain astronomy. Our group in particular, we don't do QPEs, but we're interested also in what we call basically transient flares. There have been just flares in radio-quiet Sieverts that seem to be in excess of that associated with normal stochastic variability. So we're interested in those as well. What else? I should also mention tidal disruption events. So again, our group does not do that, but we have collaborators at MPE who do work on tidal disruption events. Although one of our objects, as I'll explain, is relevant in this area. So on the left, I just have some optical light curves from of some TDEs. So TDEs can occur in quiescent galaxies, but there have been some cases where they occur in already active galaxies. And one of the most famous cases was a few years ago, this object 1ES 1927 to 654, where it was noticed that in the optical UV you have this strong increase and decrease indicative of tidal disruption event. This object was already accreted in the X-rays, but the inner disk got disrupted by this tidally disrupted material, came in, disrupted the disk, that disrupted the corona, and so the X-ray flux temporarily disappeared, and then the corona gradually reformed itself. And then in the meantime, the top panel shows the H alpha equivalent width increasing, so this was basically the burst of emission that lit up the broadline region clouds a bit later. So, long story short, the whole TDEs and AGN means that the lines between accretion categories can be kind of blurred. To me, this is really, really interesting. Just the idea that you can have just active only or tidal disruption only. You can have combinations thereof. So we're interested in these types of transients as well. So I killed it.
Second. Yeah.
All right, thanks. So basically, this is how we do it. So like I said, every point on the sky is covered once every 6 months. And so we have a threshold for detection. We cross-match with Gaia and other catalogs and verify things by eye. And we throw away the blazers because we have other folks working on them and they're extra variable. We also don't work with narrow line Sievert ones because they tend to be extra variable in the X-rays as well. We have follow-ups in the optical, spectroscopy, and photometry with various programs, SALT, VLT Force 2, and space-based programs, X-ray and UV with XMM and Swift. And we put everything into a database in order to manage new data and requests for new data and all the data that's been taken so far. And we also compare it to archival data, for example, the XMM upper limit server and public surveys, WISE in the infrared, Atlas in the optical. And so this helps us to build up the whole multi-wavelength picture as much as we can. So through mid-2022, we had over 2,000 vetted candidates. We managed to get new optical spectra on about 300 targets of order 600 spectra at various facilities. Whoops, I killed it. There we go. SALT, SAO, and VLT, Burbank Optical Telescope, and a big shout out to Marius for doing all the value reduction there. 24 objects, I think we just added a bunch more in the last few months, so probably close to 30 now, have X-ray follow-ups with either XMM or Swift or NuSTAR or NICER. And what we have found is there are of order 80 or so objects that show significant variations in H beta, but this is, I'm trying to say this cautiously because we're still trying to quantify the magnitude of the changes. In some cases, the changes are not necessarily convincing. We do have objects where the H beta line is, for example, changing very rapidly, although not sometimes disappearing completely, sometimes appearing from zero, and sometimes just fluctuating wildly. And what's also weird is there seems to be a wide range of multi-wavelength responses in that we do have some cases of diverging behavior between, for example, the X-ray and optical continuum and H beta. We have some cases where the, for example, this object right here is a case where, so here's the H beta line. It's basically, see, chronologically, you start at the bottom and work your way up. And this is an object where the H beta line disappeared, but then reappeared pretty quickly within about 3 months. But the optical light curve and the X-ray light curve are just sort of not really interesting. So this is not, so there, we have objects like this where we're still trying to sort of think about it and interpret the wide range of variability behaviors that we see. So what I want to do for the last part of my talk is just talk about results for selected individual objects of interest. And first I'm going to start off with a very bizarre object where, so this is an object that has just been published by a paper led by Xu Liu at MPE. So from ERAS1 to ERAS2, there was a strong increase by almost a factor of 100. And then when the team got follow-up observations, the X-ray flux had dropped by over 2 orders of magnitude. And continued monitoring showed, using NICER and Swift, that the flux eventually began to increase again. Sorry, I forgot to mention that, yeah. So within a week, the flux had dropped by a factor of 300, but continued monitoring through 2021 showed that the X-ray would rise again, and then was relatively stable, and then dropped very quickly within a factor of a couple weeks, and was staged again, and then you got a rise again. And so the X-ray light curve showed really extreme variability, but only accompanied by moderate ultraviolet variability. And we have these 2 cycles which allow us to make inferences about the X-ray behavior as a function of time. So as a function of time, this is the basically phase-folded light curve. This is the light curve in the bottom, the ratio relative to UV, and up the top is the photon index. So as a function of phase, it always starts off very, very steep and then gets much more flat. And this is interpreted that in the low flux state, the X-ray spectrum is dominated by thermal emission. And then in the high state, it's more power law dominated, and emission is more associated with more of compromisation. So this is an object where the corona is forming within a couple of months, but can be rapidly destroyed within weeks or so. But what's weird is that the optical spectrum is consistent with a quiescent galaxy. There's nothing going on in terms of evidence for a disk or any past AGN activity. And so the preferred explanation is a partial repeating tidal disruption event. This is definitely an object that we'll continue to monitor. But the extreme X-ray variability makes this one of our favorite objects. And the fact that it's actually published, and I encourage you to read the paper, again, by Xu Lu et al. Came out earlier this year. A second object seems to be, okay, so this is an object whose analysis was led by David Hohmann at AIP in Potsdam. The paper was just accepted. This was the most X-ray luminous transient discovered by eROSITA. So these are the images from ERS-1 to ERS-2. Things got really bright and then faded. I guess, yeah, yes, like I said, here is the brightest extragalactic transient discovered so far. The soft X-ray flux about 2 to the minus 11. And the X-ray flaring coincided with flaring detected in the optical with Gaia in late 2020. So we got a lot of follow-ups with XMM and ICER and SWIFT and optical spectroscopy, and also Atlas photometry. And this is an object that showed the characteristics of a tidal disruption event. So you have, so on the, what I have here is, this is the orange and blue of the Atlas light curve, and the darker blue is Gaia. So you have this strong increase and then decrease, similar to a TDE. The X-ray spectrum also shows, after the big increase, a decrease with some short-term variability, but the spectrum is very, very soft, down to about 5, which is more indicative of thermal emission and pretty characteristic of a TDE. However, the optical spectrum shows pretty strong characteristics associated with the AGN. So this is an object with broad normal lines. And I also want to point out this transient blue shift component that was only seen in the first spectrum. So some sort of transient outflow associated with the burst. We also have strong narrow lines associated with O3, N2, sulfur 2, indicating recent past AGN activity. So this is probably a TDE occurring in the low luminosity AGN. That's our preferred explanation.
We have no helium 2. We have no helium 2.
What's up?
Helium 2, there is no helium 2.
Sorry, there's no what?
Helium 2.
Helium 2.
You see it, 5,600. Helium 1. Oh no, that's helium 1.
Yeah.
It's helium 1.
Oh, there you go.
I mean,
Okay.
468.
That's helium 1. Helium 2 is 4,600, right?
Yeah.
Yeah. Yeah. Okay, so no helium 2. Yeah. Yeah, that.
What are the black lines? Sorry for interrupting you.
Let's see.
These below the green line, there are like 2 black. Yeah.
Yeah, this is the spectral decomposition. So I think the green is the host galaxy, and this is the AGN continuum. This might be the iron line, the iron 2 contribution. I'm not 100% sure. I have to check the paper again. We can check the paper offline after the talk. So another object, which is being headed up by my student Otto Saha, is one where we're supposed to try to figure out what it was. For a while, we weren't sure if it was a TDE, but we think it's more of a AGN flare type object. So this is an object detected as a big flare in ZTF in 2020, and also that should be ERS-3 typo. ERS-3 called the X-ray peak, and we had follow-ups with SWIFT and XMM and VLT and SAAO. So this is the light curve. The dark blue is Atlas, The other colors are optical, X-ray and UV. And just to show the non-flux calibrated spectrum. So this is an archival spectrum from 60F in 2005, which definitely showed there's an H alpha line, but no H beta. And then CAMK in 2020 showed the appearance of a blue continuum and H beta line. So the X-ray spectrum, relatively flat photon index, but interestingly no soft excess like you see in the vast majority of other radio-quiet AGN, which is kind of weird. The optical UV is consistent with a black body of order 3 times 10 to the 4 Kelvin, which could be TeV-like. Interesting enough, this is an object where the Balmer lines are double peaked. So they're fit pretty well by a double peaked Gaussian. So it's indicating disk-like accretion. So this is probably some sort of AGN flare associated with disk-like accretion in a low luminosity AGN. I just wanted to point out that, so this is these light curves. Dark blue is the optical, and the atlas are shown in red and magenta. So we also have the dust echo pretty well. And so we can model the dust echo, which is also a nice thing to do. So for more information, you can talk to Galta after the, or myself after the talk is over. Okay. So the fourth object, and I guess I'm running low on time, but I'm actually almost at the end. So the first object is an object where we had a strong increase from ERAS3 to ERAS4, where the soft X-ray flux increased by 6, but then everything faded by 6 months later. So this light curve, so the top panel are the X-rays showing a big increase and decrease. The atlas light curve and optical also showed a big increase and decrease. But this is an object that was already a persistently accreting Seaford. So it's certainly not an accretion turn-on event. So we had follow-ups, XMM, nicer, optical spectroscopy, all the usual. So what I'm showing here is the X-ray, the broadband SED fit from optical UV to X-ray, including all the galactic absorption. And basically what this slide just means is that we can explain the emission very, very well in both the high state and low state as thermal comptonization. The nature of the soft excess in AGN is still under a bit of a debate, whether it could be, for example, ion mass reflection from the inner disk, or some sort of modestly warm comptonization. In the case of this object, it definitely is modestly warm comptonization, and the soft excess changes very, very drastically between the two observations, as shown by our XTE data, XMM data. And so this flare seems to be driven by a change in the accretion relative to Eddington. From the peak state to the low state, the luminosity drops by about a factor of 4, very roughly, as the flare subsides. One other interesting thing in the optical spectra, so what I did here is I just have an overplot of the optical spectra from, see, black is the peak of the flare in summer of 2021, and then the other two are just a few months later, actually not even that, just a few weeks later. So here's our H beta, oxygen 2. The helium 2 line actually was very, 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 very strong in the force 2 spectrum, but then completely faded by 6 months later. This slide needs to be updated. So we were thinking, okay, our thinking as of the last time I gave this talk was that the helium 2 line was just tracking the flux above 54 eV. Our thinking now is that helium 2 just has a much stronger responsivity compared to the Balmer line. So a small change in the ionizing continuum can lead to a modest change in the longer line flux, but major changes in the helium-2 flux. So, sorry, the slide should be updated. But so it's interesting that this is sort of almost a, okay, it's kind of grasping here, but it's a changing look AGN in the sense of the helium-2 line. So this object is being written up by my PhD students like accretion, and we hope to have it submitted relatively soon. And the last thing is we have like a transient redshifted feature. So maybe this is a signature of some sort of inflow or failed wind. And again, this only appears in one spectrum. So just to finish up, the last object is something completely different, but it's something we can also use eROSITA for. We can monitor the soft X-ray emission to look for major changes in the soft X-ray flux associated with when a cloud of gas drifts in front of the line of sight. I didn't put any of this in the introduction because it would have taken a long time, but this is one way we can test clumpy torus models. So if the torus is not a smooth donut, if it's made up of clumps, then these clumps can drift in front of the line of sight. So this is an object where from eROS1 to eROS2, the soft X-ray flux dropped by about a factor of 15 or so. And so we followed it up with SWIFT and XMM, and the flux remained low through mid-2021. And I started to write up the paper, and then for eROS4 in late 2021, suddenly the flux came back again, so we had to get another XMM observation. And so I just had to make more changes to the paper and started to write it up. And then in early 2022, we managed to get eROS5 just before the shutdown, and the flux got really low again, so we had more follow-ups. So basically, we have these very strong soft X-ray flux variations on timescales of months. And the follow-ups with XMM show very, very clearly in the X-ray spectrum that this is due to variable obscuration. So the top panel is XMM3, which is the brightest state, unobscured. It's just a typical CFERT X-ray spectrum. But the lower two panels show the X-ray spectrum during the low flux states, and they're completely consistent with partial covering obscuration by columns of order 10 to the 1 to 10 to 22, 10 to the 22, 10 to the 23. And so this is definitely a case of variable obscuration. And get back here. Oh, I don't have, oh, no, that's right. This is correct, sorry. And so basically the constraints on ionization and time scale, you put it all together, you infer that these objects that are causing the occultation are probably residing at radii commensurate with the broadline region. In other words, these could be broadline region clouds. The reason why they take such a long time to transmit across the line of sight is because from the optical spectra, we get that the black hole mass is very huge, like 4 times 10 to the 9 solar masses. So even a transit by a broadline region cloud at order of 100 light days or so is going to take months in order to complete. With the optical spectra, the optical UV continuum photometry, we see no evidence of reddening due to dust, so these clouds are non-dusty. So that could also support that they're lying inside the dust sublimation radius, inside the broadline region. So that's what these bottom plots are. These are just the optical spectra showing. Here's H beta showing not much change in H alpha, and H beta is not really doing much of anything. So there's really not much going on in the optical spectrum and neurooptical photometry, which is what you expect if you have a compact corona in an extended broadline region, and one of the clouds is occulting X-ray, but it's not going to impact any of the other tens of thousands of broadline region clouds. Excuse me. So that is work that I'm trying to finish up, and hopefully will be submitted soon. So just to recap the work done or in progress for 5 intriguing events. So if you're interested in TDEs and partial repeating TDEs and how an X-ray corona can be formed and rapidly destroyed on timescales of weeks to months, then I encourage you to look at Shu Liu's paper, A669, A75. If you're interested in TDEs and AGN, then I encourage you to look at David Homan's paper, which is in press and it's an archive. So it's an object, again, this was an object that has characteristics of both TDE and AGN. And so it's like Krishnan is preparing her paper on a Clarity Seifert consistent with thermal composition and this changeless helium line. And Toshibata Saha is preparing his paper on an object that's showing a flare in disk-like accretion, and also tracking the dust echo. And the change in obscuration, Seifert, is what I'm doing, so if anyone's interested in talking about clumpy torus models, I can certainly talk about that. And there are many, many other objects that we are still tracking and really trying to nail down the nature of. Train the response timescales and track the response of the corona and the broadline region. Bigger picture, this is actually my last slide. There's a lot of work that we're still doing quantifying the broad range of variability responses in the X-ray and the optical spectra. And we will be moving towards the large-scale statistics of how many objects we have that are showing changes. And we'll be moving from there to getting the first X-ray estimates of duty cycles. And related to clumpy torus models, we're also going to try and do a statistical survey of obscuration via hardness ratios for a subsample of the brightest Seiferts to obtain constraints for clumpy torus models. And so that's it. So that's it. So thanks for your time and happy to take questions.
Thank you. Thank you, Alex. Questions? No.
Thank you for the questions. Sorry, I can start. So, thank you for this. I was wondering, when you said that you do the cross match when you find the X-ray results, when you said that you do cross match with Gaia, do you do just with Gaia the database or the data inside those?
I'm actually not sure. So our colleagues in Potsdam who do this. I think I'm going to have to refer you to them for the details of it. But there are multiple catalogs that it's not just Gaia.
Yeah, specifically for alerts. I mean, for Gaia alerts because it's not in a database. It's separate. I mean, it's kind of separate. So I'm just wondering if you use them because it would be really useful.
Yeah, I'm sorry, I'm out of the loop on that. I'm going to have to refer to my colleagues on that. Sorry.
There was one which had some Gaia data, right? So it was found as a Gaia alert for sure.
Yeah, that one was, yes.
Yeah. So now I was wondering if the others were checked, and that would also be my question. But yeah, we can take a look.
Yeah, I mean, I think they are, but in terms of alerts, I think that object might be the only one.
Okay.
I don't know. Sorry.
Yeah, it would be interesting to check all your targets, whether they've been alerted by Gaia, because Gaia is close high, and everything brighter than 20 is being alerted on. So it would be interesting to. Any more questions here?
It'd also be interesting in terms of like what the thresholds are for a Gaia alert versus what we consider to be an interesting object.
Yeah, exactly.
Got the question.
Yeah. So I was wondering, because I was not sure if I could understand when you were showing the luminosity versus the photometric, photometric versus the photon, right? So the changing the paper, do they actually then move to the line from broad line to narrow line region with luminosity as well?
I think it was here by Rwanda 2019, where I think the answer is yes. Somewhere around there. I think the answer is yes. Victor might be able to answer that question better.
The reason why I ask, I mean, I can, because I was wondering if, for example, if you get the spectrum of only when in optical the event is at the peak. So if you don't have a kind of spectrum to compare it to, you can use emphatic photometry, right? Because there's no automatic observations. So if you can,
hopefully,
if you can kind of assume if this is a change in the phasor or not.
Yeah. I think the paper by Rowan et al. 19, they do have archival spectra.
Yeah.
And so they can confirm.
But
you're right.
Like events where I only have spectrum at the peak, and there are, for example, broad line AGN, and because you cannot compare them with their cover because it doesn't exist, right? So if there's a way to see if this is a changing to AGN or just normal broad line AGN that for some reason did one magnitude,
Yeah, and this is also an issue we have for a lot of our objects. Yeah, we if it's on at 60F, or some other days we don't have it.
You're talking about the hardness of variability connected with variable obscuration, yeah? For example, photon index, it's about the same like hardness, yeah? You mean photon index.
Right.
Yeah, so it's well known that it is anti-correlated with luminosity, mostly. It's not connected with...
yeah, I mean, it's a modest effect. For the object I'm studying, the first, basically, how do I say this? The XMM data were really, really useful for our case in basically deconvolving the power law from the obscuration. Without that, it would have been extremely difficult to confirm it. So in the absence of high energy resolution X-ray spectra, it can be difficult to do.
And also when luminosity is dropped down significantly, the photon index start to grow and get the same value like in high states.
Well, I mean, if it drops,
it's the type of variability of hardness. You know, publication exists about this.
Right. Because maybe with the ADAP is forming.
Yeah, it's also explanation is usually without obscuration. It's elimination of reflection and so on.
Yeah. But I'm not. I mean, you can correct me on this. I'm not aware of any object in AGN that is proven to be going from the thin disk regime and then accreting down in the REAF regime. I mean, it's statistically looking at samples of AGN, you do these two branches.
The analogy was in solar masses, X-ray sources. It's the same.
There you can't see with individual objects. So there's no reason not to expect it for AGN.
But it was suspected also, in some publication, but not so many.
So it is helpful to know what side of the critical accretion rate you're on. In the case of the paper I did 10 years ago in variable obscuration using the RXTE sample, we knew that the vast majority of objects were above this critical rate, this critical transition rate.
Okay, that's a question. Yes.
Yeah, thank you. Thank you very much, Alex. This is really exciting. I mean, I'm very much impressed with how many objects you kind of have as a candidate. So it's around 1,000, right? Or something like 600, would you just... Can you go back to this?
Yeah, it's like 2,000, I would say, candidates.
2,000.
Yeah, but this is not candidate based on optical spectroscopy, it's candidates based on the X-ray variability. And then of those,
you said right around, you have around 80.
Something like that, 80 or so. Yeah.
I was just wondering, you said that you discarded lasers because you some other people are doing, and then you said you discarded narrow-line CP1, and I just wonder, is someone follow up on this narrow-line CP1, because that would be also very interesting to see.
Yeah.
Is someone working on that?
I don't know.
I mean, you're not thinking maybe to consider some of your targets to be these ones, no?
Well, I mean, a few of our targets did end up being narrow-line Cedar ones, and the variability just seemed to be consistent with normal variability.
Oh, okay. So
There was nothing going on in the optical spectrum, just very strong X-ray continuum variability. So we're trying to filter out against the normal ones.
And when you showed this spectrum, I just, if I may just comment this, because there's just a 1 month difference between the red salt spectrum and the force spectrum, even less than a month. Because I think it's 13 January and 8 of February.
Yeah. Yep.
That seems very highly unlikely that this change. I mean, I'm aware that salt spectroscopy is quite challenging. So I just wonder how reliable is that? Is this work published?
No, this one, no. This is one of our.
So if you use the photometer to calibrate the stuff, it's reliable.
It was calibrated using photometry. Yeah, calibrated this using photometry.
I didn't do any of the optical reduction.
Yeah, I just doing the standard calibration, but you can use the photometry to be sure of that.
But this is then incredible.
Yeah, we see some variability, look like variability in forbidden line. What is in oxygen line is clear a few times variation. So something wrong with calibration, or it was.
I mean,
different slits probably.
I think these spectra have not been rescaled by the oxygen line, so I wouldn't look at the oxygen line flux here.
But definitely, when you compare, you should scale based on the oxygen.
Right? These are not scaled or anything.
Maybe different slits, aperture.
Different slits, different absorbing conditions, different everything.
Resolution.
Different energy resolutions.
Yeah. But the calibration is not accurate enough. So it's usually forbidden line is needed for correct calibration,
right?
For sure. Yeah.
These are certainly not corrected.
Yes.
This is just the raw spectra.
Well,
it is something that we do. I just didn't plot it here. This is not publication ready yet.
Okay.
And I suggest to move this discussion because it seems it requires a little bit more time, which not all of us have it. So I encourage to stay after the seminar and discuss it. But let's stop here and let's thank our speaker again. Thank you. Thank you for joining, and we can now continue the discussion. Thank you.
Yeah.